We introduce our paper titled Pose-Guided Self-Training with Two-Stage Clustering for Unsupervised Landmark Discovery. Let's begin by outlining the problem statement of unsupervised landmark detection, or ULD for short. Given a set of images of a particular category, like human faces, the objective of ULD is to learn a set of landmarks in the image ROI that are consistent across image variations like pose, occlusions and lighting. We do this by training a network to predict the landmarks. Each color represents a particular landmark across images. Challenges to the ULD include occlusions, pose variations, face type variations, image quality, etc. In our paper, we use a pre-trained stable diffusion model to learn unsupervised key points. This approach is inspired by recent studies showing that such models implicitly encode key point correspondences for various object categories. Throughout the paper we use the words landmark and key point interchangeably. Recent works like diffusion hyperfeatures and LDN correspondences have explored the feature representations contained in diffusion models trained on large amounts of data like stable diffusion for tasks other than image generation. Both these methods learn correspondences with minimal or no fine-tuning of a pre-trained stable diffusion model. Shown in the slide are the correspondence results obtained by both methods. As can be seen, provided with a key point in one image, they implicitly capture correspondences across other car and bird images. It appears that implicit to the image generation process is feature representations that provide key point level differentiation of the various parts of the image. Inspired by these results, we explore the use of stable diffusion for ULD. We use this strong prior as the starting point of our method. As our method makes use of diffusion models, we now introduce them. At a high level, the idea behind diffusion models is simple. They take an input image x0 and gradually add Gaussian noise to it through a series of time steps as shown in the image. This process is called the forward process. Afterward, a neural network is trained to recover the original data by reversing the noising process. By being able to model the reverse process, we can generate new data. This is the so-called reverse denoising process. Diffusion has been shown achieve state-of-the-art results on generative tasks. Stable diffusion is a multimodal network taking as input images and text prompts. Throughout our presentation, we assume empty text prompts as input. Stable diffusion generates features across the various layers and time steps of the diffusion process. We aggregate them into a single feature map using a neural network, where the relative importance of the features across the various layers and time steps are learned. Given a set of feature maps from the diffusion process, the aggregator network combines them into a single descriptor map, learning the relative weights for the different feature maps via backpropagation. We use the aggregator network used in diffusion hyperfeatures. Going forward, we combine the feature extraction from stable diffusion and their aggregation via the aggregator network into a single aggregator network operation to avoid clutter. We now provide an overview of our method. As a part of pre-processing in stage 0, we train our network to predict key point locations using the silk training scheme. Next, in stage 1, we do a key point level clustering-based self-training. Learning clusters that capture key point level information consistent across images across the training set. We term this stage as DULD. Finally, in stage 2, we propose learning an image level pseudopose based on the predicted key points from the previous stage and use this to their locations between images with different poses. We term this stage as DULD++. The silk pre-training involves appending a detector head and a descriptor head to the feature backbone. The detector head is trained to detect key points while the descriptor head is used to extract feature vectors subsequently used in downstream tasks. This pre-training is done to make the network predict semantically interpretable and localizable key points. Additional details can be found in the paper. Self-training involves using the network's own predictions for training. We use a clustering-based self-training scheme to train the network to predict key points. DULD is a simple training scheme that alternates between generating clustering-based pseudo-labels and training a network for ULD. The aggregator network takes as input an image. Then the output descriptors at the key points from all images of the training set are then clustered using k-means. Then the key points per image are pruned, leaving each image with n key points. The clusters of these key points are the pseudo-labels used for training the network. Additional details can be found in the paper. DULD by itself shows substantial improvements over the previous SOTA methods. But it occasionally fails to capture extreme pose variations and is sensitive to occlusions like hair and so on. To overcome this limitation, we propose to use the predicted key points to encode global level information, which would help overcome poorly localized or incorrect key points. Each key point intrinsically contains local information. The aggregated position of these key points in a particular image, however, captures global information like pose and orientation. Therefore, accurate pose information can aid in learning accurate key point positions and vice versa. This inspires our proxy task, where we use the output of the detector heat map to learn an image-level encoding like pose through a proxy task. We realize this is a VAE. The VAE along with the upstream network are trained via standard elbow loss in addition to the previously used losses. We show in the paper via cluster analysis the latent codes predicted by the VAE capture pose information. We use this to further improve key point localization via a two-stage clustering-based self-training. Finally, we can use both the key point and pose pseudo-labels for unsupervised landmark detection. DULD++ starts off with two-stage clustering. As mentioned earlier, clustering the latent codes obtained from the proxy task captures the pose information. We initially, in stage 1, cluster the latent codes obtained from the pose-guided proxy task. In stage 2, we cluster the key points for all the images whose latent codes are clustered together, thus key points with similar poses are clustered together. We get two sets of pseudo-labels from the two-stage clustering, the first for the latent codes and the second for the key points. We use these two sets of pseudo-labels to supervise the network with contrastive losses. For the detector head, we first discard the VAE decoder. The output of the VAE encoder is supervised via the latent code pseudo-labels, while the descriptor head is supervised via pseudo-labels for the key points. Additional details can be found in the paper. We alternate between these two steps, training the network using own predictions to improve its predictions. The results and additional ablations can be found in the main paper. The code and models can be found in the link provided. Thank you for listening.